Hello and welcome to Nerding Out with Queens of Physics. I'm Brittany Kamai.
And I am Jen Helsby, and we are two friends who met in graduate school doing our PhDs in astrophysics. And we have decided that we want to hang out over Zoom and read some physics papers.
Yes, we love hanging out with each other. We have a lot of fun. We get into the nitty-gritty weeds of physics, which is a great journey to be on. And so today we're going to be talking about kilonova and sharing our discussion with all of you out in the world. So
Yeah,
Jen,
so apologies in advance. Just kidding. Okay, so let me share my screen where we were reading this. We can see this, yeah?
not yet.
Yeah?
Yeah, yeah,
Okay,
now we
so
are.
okay, so this is a wonderful review paper by the cool guy Brian Metzger. Never met the guy,
He's
and
he's really nice.
oh, you know it. Okay, so
Yeah.
shout out to you out there, Brian. Um,
Thanks, man. Thanks for writing this.
and so yeah, so what is a kilonova, which I actually didn't know until reading this paper. So when there is a neutron star merger or a neutron star black hole merger out there in the universe, they can produce kind of multiple astrophysical signals that we can detect. So here in the abstract, it describes, okay, these events are prime sources of gravitational waves, but they also produce short gamma ray bursts, which we're not really going to talk about, like a few seconds. That's what the short means in that short gamma ray burst. And they can produce a thermal emission, kind of like a supernova, which is an explosion of a regular star, which can decay over days or even weeks. And that is what a kilonova is.
Yeah. I'll jump in a little bit. So we're living in a really neat era where when we study the universe before, it was just measuring the photons, like the light that's coming in and trying to figure everything out. Now we have gravitational waves, these ripples in space and time that are being produced from stuff that Jen was talking about. So it can be black holes smashing into each other or this other like leftover deadness from a star, the neutron star. And so what's interesting is around black holes when they smash into each other, there's not really much matter or any other stuff laying around near it. But with neutron stars, they're made out of matter. And so when they smash into each other, they're having this other process that's making these heavy elements in the periodic table. And so for astrophysics, it's really neat because hydrogen was created in the Big Bang, helium, all of the elements that kind of get to iron were made during the lives of stars. But to get to the heavier things, so beyond iron, you need processes like this where you smash together neutron stars. So that our process that Jen's talking about is the kind of like gathering of all these extra like protons and neutrons that are cruising around to make the heavier elements that we have in our life. And so that's kind of like helping contextualize some of the reasons why us nerds are actually really excited about kilonova, because you have two signals, one from gravitational waves, one from electromagnetics with the light, and then you're telling this whole wild story of like the periodic table. So there you go.
Nice. Yeah. And so one of the things we learn in this paper is that these neutron star, or the subset of neutron star black hole mergers that can produce a kilonova are not necessarily the dominant source, but one of the big sources of these R process elements that Brittany is describing. So, things like cesium, all of the spicy stuff up here on the periodic table, that's what's made in these events. Okay, so maybe we should kind of start at the beginning. So first we learn about gravitational wave events in general. And so through gravitational, what are gravitational waves, Brittany?
Yes. So it's a prediction from general relativity that mass is anything with mass. So like our hands have mass. As soon as it's accelerating, it's changing space and time around it. And so if next time you're at the club and you're dancing around like this, you're actually making gravitational waves. And it's not so much that like you're literally changing the width in the ticks of a ruler. So you know, like when you look at a ruler and there's little ticks in it, that's like a centimeter, 2 centimeters, whatever. Like when we're talking about space and time moving, those ticks are actually moving back and forth. And so that's the type of thing that we're looking for, is those ripples that are getting produced in the universe. And you need massive objects to be able to make something that we can kind of sort of measure. Not kind of sort of actually measure. What the hell am I talking about? We measured all this. Um, but I'm saying that the signal is so tiny. So like you need a massive object, something that's like way more massive than the sun, to be running around each other and making these ripples in space and time, so that when they get to Earth, they're about 1,000 times smaller than a proton and how big that wave is. So if you ever looked out in the ocean and saw like little tiny ripples, it's like way, 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 way tiny. That is a very random way of describing gravitational waves. But so that's the reason it's not just that black holes and neutron stars are the only things creating it. It's that the combination between what we can measure and what this technology allows us to get to are these types of objects. And so that's that was my chair. That was not me.
Oh, wait. Let's make sure the listeners know that.
I was like, oh my.
And I would like to flag that you know, what was implicit in that is that you were calling them supermassive when they're emitting gravitational waves in the club, but okay.
Yes, so I was somewhere in the club. Yes. Yeah, so I mean, like the thing that Jen's showing on the screen is like the way that we talk about those two objects that are dancing around each other. And so I have like one hand I would call M1 because that's just this first mass I have, and then the other hand I would call M2. And when we put those things together to try to figure out how big of a gravitational wave that would produce, we call that thing a chirp mass. And so that's a dynamical mass that's going to be producing some waves in the club called the universe.
Okay, so we see this equation here. So M1, M2 are the two masses that Brittany described. And apparently there's this one event that all the gravitational wave folks are extremely hype about. GW 170817. Is that how we call it? Okay, cool.
Telephone number GW 170817. And that's the date. That's the gravitational wave event on that date in the year, month, and day. The best way we know how to talk about it.
And this is the first gravitational wave event that had electromagnetic emission of this type associated with it.
Yeah. So first we're like super hyped that we actually measured gravitational waves at all. So that was like a huge, huge discovery. And then those are two black holes smashing into each other that were way bigger than predicted. And then a big, huge thing that people in this field have been hoping for, and the whole time they're building these crazy detectors, is to be like, okay, can we measure gravitational waves and electromagnetic signatures at the same time? And so these types of events of these neutron star mergers were like this other kind of wild, like holy grail of like observable we wanted to get at. And what was amazing about this, I'm like getting like chicken skin, is that like not only did we measure it in gravitational waves, we literally measured it in every single wavelength that you could possibly measure in, from gamma rays all the way out to radio, for like weeks after it happened. And so it's just so amazing that we were able to like, and it's so trippy too. It's like you had to coordinate across every single electromagnetic counterpart to be like, can you turn your telescope there at this part of the day? Because, you know, just because the event happens, we need the Earth to be turning around to have night on one side of the planet to be able to look up at that spot, and then to have detectors even capable of seeing that part of the sky. And so that's why people are so hyped about this, is like for all of those reasons, that we had our space-based telescope, all the ground-based telescopes, and then able to get this like richness of information about like what, like, does it actually produce those heavier elements, those lanthanides? And it's like, they do. So that's why everyone's so stoked about it.
Yeah, the paper says later on that like a lot of telescopes were able to follow up, but right after the event occurred, it was over, I think, the Indian Ocean. And so obviously there's very few telescopes over there in the ocean, precisely zero. And so it took, a few hours, I don't know exactly how much, for people to be able to get on the object to take measurements. Okay, cool. So we have these kind of source of gravitational wave events. We can measure this chirp mass from the waveform, right, Brittany, of the gravitational wave event, and that constrains the masses of the two objects. So then Brian here goes on to chat a little bit about why we care about these events. So two other reasons are when we measure one of these objects, it tells us the rate of these neutron star, or neutron star black hole events in at least the part of the universe that LIGO can currently observe. And that in turn then tells us, okay, given the, X amount of heavy elements are produced in a single neutron star merger, can this account for the abundances that we see in the universe in general? So that's kind of one pretty cool measurement. And I guess the other big reason why we care about gravitational wave events is that it allows us to test general relativity, which is Einstein's theory of gravity in this sort of extreme strong field regime. I believe, I'm sure that I think QAnon has something else to say, but I believe we don't have the ability to make black holes here on Earth to test that regime, but out there that's the cool thing about astrophysics. There are many extreme physical scenarios that we cannot create here on Earth, but they are happening somewhere out there in the universe. So if we can collect that data, that's great. Okay. So the other kind of thing that I mentioned a little bit was that these merger events also produce two other, so there's the gravitational wave event that happens, that we can see first, and then there's a gamma ray burst. Is actually a nice plot here where we can see so this is now a black hole remnant. There's a little disk here. And then depending on the angle at which this is happening, we can see if we're aligned right along this highly collimated jet, then we're going to see primarily the GRB. Here's the time scale, 0.1 to 1 second. So then there's gamma ray bursts. And then as all of those gamma rays hit into the surrounding medium, that's going to produce lower energy emission over a much longer time scale.
Yeah, and what's neat too is that before this observation, then the scientists in the gamma ray community started measuring all these very short period gamma rays, and they didn't understand what it was correlated with. So there was this whole flurry and discussion of what could short GRBs be coming from. And so it was amazing that when this merger happened, that you're able to see a short GRB associated with it, which then kind of, there's still discussion on is it really associated? Is it not? But it is this really cool connection between, in another space in astronomy and astrophysics, an open question that's coming together with this object.
I guess the less good part about the GRB is that you do have to be aligned, the observer angle has to be aligned pretty closely to be able to see at least a lot of GRB emission. However, as this cartoon demonstrates, if you're at these lower observer angles as measured from the jet, then you can see this kilonova emission from material that is ejected from this merger event. And that is, so timescales here, you start to see it days to even months in very low energy wavelengths.
Yeah, and it's super neat. It's kind of funny to unpack this picture, because it's like those lobes are just this mass, it's this distorted mass that's you started out with these two objects, they're smashing into each other, and you got this like extreme stuff around it. And so it's like a time lapse picture. It's like the thing smashes into each other, some bleh is going out here, and then that's spreading out even further. And what's amazing is that they end up in different wavelengths, right? So really close by, it's like the shortest wavelengths, then you get to optical, and then you get to radio to be able to understand how this whole process happens. And in that time scale, it's like you're creating these heavier elements because they're like, cool, there's a bunch of neutrons cruising around. We're going to just gobble each other up and just smash into each other. That's really what the R process is. And I'm not
It's like you're reading a textbook.
This is what they really say when you're going to get all your degrees. Just smash it together.
I guess the other like challenge with making these kind of observations is, and I think he talks about this somewhere up here, is the gravitational wave, like the location of the gravitational wave in the sky is not super precise currently. And so that's difficult for an optical astronomer because you might have to, unless you have a really wide field telescope, and even then you may need to kind of scan around a little bit and take multiple exposures to try and find if there is an optical counterpart.
Yeah, I mean, so the difference between like the way a gravitational wave detector is like, so like your ear, right? Like you can hear a sound over there, and then you want to go look at it, which is what the telescopes are. And so each detector has like some pretty wide opening angle, like each gravitational wave detector has a wide opening angle on both sides. So like each detector can measure above the earth and below the earth. And so then having multiple detectors around the earth is like having multiple ears on your head, which is a really creepy image, but so that you can be like, oh, it's kind of more in this spot. But as Jen's saying, for the telescope folks are like, oh, that's like a huge part in the sky. Like that's way too much. So that's really what's interesting when sometimes we don't measure things in certain detectors. It actually helps a lot for the optical follow-up because they're like, okay, cool, it's not in these parts of the sky. And that's a big area of work of trying to minimize that like location area to help our optical follow-up.
And I guess being able to see if there is a GRB associated with the event, that helps a lot because the gamma ray telescopes, Fermi, etc., should have a much better resolution in terms of, okay, it's here on the sky, to help optical people figure out where the the lower energy electromagnetic emission is.
Yep.
Okay, cool. So we did see a gamma ray burst and the Fermi and integral satellites. Probably both space-based. I know Fermi is.
They are.
Okay, great. Detected a nice GRB. They couldn't find the exact location. However, others were able to. Yeah, so nucleosynthesis is the general process by which the various elements are created. And so in the very early universe, so there's a process called Big Bang nucleosynthesis by which a bunch of elements, very light elements, were created, so mostly helium, and like very small amounts. Pardon?
It's mostly hydrogen.
Well, yeah, mostly hydrogen. That's just protons,
Oh,
isn't it?
and deuterium, right? Like deuterium, yeah, but not helium, right? Like there wasn't
No,
that
it's like 75% hydrogen. There's going to be a little bit of deuterium, which is stable, and probably, certainly a bunch of tritium, which is unstable, would have been created, but this half-life is like 12.3 years, and so all of the like Big Bang tritium is certainly gone. And then I think like roughly 25%-ish was helium, and then little sprinklings. This is back of the envelope numbers, FYI listeners. Little sprinklings of lithium and beryllium were also created.
Oh, wait, I got a question.
But yeah, it was mostly hydrogen and helium.
So how do we know which hydrogen is like Big Bang nucleosynthesis or which
Yeah, we
helium?
don't. We don't.
So I guess we don't know
We can
which,
predict how much helium was created during Big Bang nucleosynthesis, and
yeah.
then we can measure the abundance of helium around in the universe, and then we can calculate, okay, there have been so many populations of stars since that
Mhm.
time. Here are the nuclear processes that were probably occurring in those stars. We do
Yeah.
understand like stellar nucleosynthesis pretty well, and so then you can predict abundances from that and see if they match up. Obviously, if you had more helium than predicted observed in the universe in present times, it means there's some additional source of helium, which I believe is not the case. I think that they are consistent.
So do definitely going off topic, but that's just part of this
Yeah,
ride.
that's okay. Yeah.
But like, do first stars, like the very, very first stars that were ever created, they already start out with helium in them?
Well, they'll have some helium in them, yes, from the Big Bang. Like all of this Big Bang nucleosynthesis happened within a few minutes of the Big Bang.
Yeah.
And so by
Yeah.
the time that stars are able to form, yeah, it's like, there's tons of hydrogen, and there's still helium available. But the hydrogen, I guess the deuterium will start burning first, then
Yeah.
hydrogen, because I think it's easier to overcome the Coulomb barrier or whatever for deuterium.
Yeah. I guess like I just neglected or maybe just threw it out of my head about the Big Bang nucleosynthesis creating the helium. I mean, it makes sense. Like there would be some fraction of it, but I was like, it's just from
Yeah.
like stellar nuclear physics. So like or nucleosynthesis. Come on with all these words.
George W. Bush has entered the chat.
But yeah, I thought it was just like in the lives of stars and like, well, that's predominantly the helium we have now, right? So okay,
Yeah,
cool.
I mean, I think it's obviously an accurate statement to say that heavy, certainly all the elements beyond even like lithium. I probably the vast majority of it is from stellar nucleosynthesis. Citation needed. That's a guess.
So like every
We could
battery,
calculate it, but that's for next episode.
okay, great. Add that to the list. So every battery is coming from a star, you know? I mean, well, everything is coming
Yeah.
from a star, but like, okay, anyway, I will stop to distract. But I mean, like, this is an
No, I mean,
important,
this is like a very interesting process that
yeah, because
it's like, where did the elements come from? And as we're learning from this paper, there are a lot of unknowns. Like now we know enough about stellar nucleosynthesis, like Big Bang nucleosynthesis got nailed down pretty good. Stellar nucleosynthesis, we're able to produce, everything up to iron, nickel, stuff like that in stars and white dwarfs exploding. We can simulate that stuff now. But the really heavy elements produced by the R process, and there are a few other processes like it, I believe, where you capture neutrons. That's still like an area of active study, it seems.
yeah, I mean, like, I think too, it's like you can explain them from like singular stars, right? Like one star's life will get you this far. And then you have supernova explosions that get you kind of further into the like higher elements than iron. But then now when you have two of them smashing into each other, then you can get to even higher things, which is what's exciting about these
Yeah.
objects. Yeah.
I think I think this is in the paper, but there are some core collapse supernovae where I think it is thought that the R process can occur, like if it's a neutron rich environment. Yeah. So, but I think it's not yet known like what the ratio of like neutron star mergers to and neutron star black hole mergers is to like core collapse supernovae in terms of explaining the abundances of our process elements.
Yeah.
You gonna say something?
No, I was just like, yes, that's it.
Yes, preach.
I'm ready. Let's
preach
go.
that nucleosynthesis.
Yeah.
Okay, so what's going on with the R process? So the R process, the R stands for rapid. So this is a process by which there is a lot of neutrons in the environment, and heavy nuclei are able to capture neutrons before they decay and thus become bigger nuclei. And so that leads to this spectrum of heavy elements. So here it's saying the timescale for neutron capture is shorter than the beta-decay timescale, and beta-decay is a weak interaction.
It's like that game show where like the money falls from the thing and you gotta like grab it all before it like goes away. You know what I'm talking about?
Oh, that famous beta-decay show. No, I see what you're saying. Yeah, it's exactly like that.
Gotta get those dollars falling from the sky. That's what it is.
Yeah, there's neutrons falling from the sky, and the nuclei just have to capture them
exactly.
so that they can become
they can get rich.
Get it?
Oh my god, you heard it here first, people.
Yeah.
Neutron rich. Oh my god.
At this point, nobody's watching this.
Oh, thank goodness.
Just kidding.
It's all good. It's all good. For those diehards right here. Okay, we're continuing on.
So beta decay is when a neutron can decay into a proton, an electron, and an electron antineutrino. And so the neutrons the neutrinos just float off there. But the protons and electrons would stay in the plasma and reduce the probability that neutrons will get captured. Obviously, if you're a nuclei, you're made of neutrons and protons, and so it's harder to capture a proton because of electrostatic repulsion. So you've got to overcome that barrier before you can get absorbed. So
yeah, it's like those people you're just like, but I really gotta hang out with you. I gotta come over to Sperry, you know.
I'm not familiar with that. No, I'm just kidding.
All right. So then we like nerd out and we're like, you know what? We're just gonna put this into some number that we're gonna call the electron fraction. That's why. Y sub E.
Yeah, so Y sub E is the fraction of the number density of protons relative to the sum of the number density of neutrons and protons together. So you want this electron fraction to be low to have a lot of neutrons. So ideally, so here he says, matter with a neutron excess, which means Y sub E is less than 0.5 is something that we need for the R process to occur. And so then we go on to talk about core collapse supernova, which we mentioned before, where there's only a few scenarios, at least based on what we currently know, where you can have the R process occur, where these kind of neutron-rich environments can occur. So one is if you have, and this is like pretty cool, I would like to understand more, neutrino-heated winds from little baby neutron stars that have just been created. So presumably there is a wind that's kind of stripping neutrons, I guess, maybe off the surface of this thing. And that could be a process of this thing being this proto-neutron star. And that can be a source of our process elements. Another one that's pretty cool is if you have a magnetar, which is or an ultra-strong magnetar, where you have a neutron star with a very strong magnetic field. And that can also be a source of our process elements.
Just a cool name, right? Like, I work on magnetars.
Yeah, it makes you sound like an X-Men person.
Absolutely. It's like Magneto's like protege.
Yeah, he was actually someone who studied magnetars, so that's how he got his powers.
Exactly.
Disclaimer, not true. I made that up. Okay, so yeah, here he's saying, based on how it seems like it's pretty hard to have the R process occur in these core collapse supernovae, and the rate of neutron star mergers, and what we think the abundances of R process elements that are produced in these neutron star mergers, it's probable that it's that the neutron star mergers are a pretty major source of R process elements. Okay. There are a couple of like open questions that were pretty interesting. Yeah, here we go. So one of the challenges to this picture that we just described of these mergers being this primary source of our process elements is that when these neutron stars form, the binary system can get kicked from the galaxy. So when the merger occurs and the associated kilonova, the heavy elements that are produced don't make their way back into the galaxy to pollute the gas with heavy elements. There are processes by which gas gets in and out of galaxies, and so maybe there's some work that someone is doing to simulate that.
Yeah, and that's like such cool stuff because I mean, a lot of the simulations are, you know, like two body systems, right? But then it's like you'll get these two body systems and then you can have enough stuff that's kicking it out and away. And you can even like kick out like other objects and stuff that are like just like peace, I'm out of this galaxy now just because this thing happened. And so that's like all of this really cool work that goes on. In fact, Enrico Ramirez Ruiz does this with his awesome colleagues who make this magic happen. So we should bring him on our podcast to talk about it.
Nice. I'm into it. Okay, should we discuss a brief history of Kilonovae?
It's up to you. Whatever you feel is being called forth to the people.
Okay, well, I feel like the people definitely want to know about a brief history. So it sounds like there were two authors who suggested that the decay of our process elements could produce or could power this transient emission that you could potentially see in the electromagnetic. And so equation 4 is a heating rate of the ejecta, where they have 3 parameters. So it relates to the mass and the time after the merger, which makes sense that it's 1 over the time because it's going to decay as the radioactive decay occurs.
I also really love that we have stuff like F is a free parameter. You know what? I'm just gonna add this thing in here.
Yeah. Well, I think that was something that in the early days of kilonova was kind of problematic. So in their early studies, it sounded like they picked some values for F that led to super high luminosities. And I guess it over predicted luminosities, as people ended up being pretty reliant on those choices of this free parameter F. And so Metzger, cool guy Brian, with derived luminosity predictions based on I guess a calculation of the R process nuclear reaction and the dynamics of the ejected materials. And so that was able to give a much more realistic prediction for the peak luminosity.
Wait, I missed this piece.
So this is where the term kilonova comes from, because what he got was a peak luminosity 1,000 times brighter than like a nova.
So I guess that's yeah, I remember hearing that, but thank you for bringing that. But the piece that I don't understand is like the first prediction is saying, here's our guesstimate.
Yes.
Here's our guess, but I mean, like, I think
we could look at the paper to like, I'm sure there was a better justification than just a full guesstimate, but yeah, they picked some.
No, I mean, like, guesstimates are the thing, but I think like the piece I'm trying to work out is that these are the R processes, and this is the relationship between how much mass is getting lost, and then it's going to be a certain brightness. Is that what this?
Yeah. So they're saying, okay, the heating. So they're saying the heating is the main source of energy for this transient emission, and that's related to the mass, the time since the merger has occurred, and from that you can compute what the luminosity we should see is.
Okay. I guess I'm not okay. Fine, but which is the piece that they're, because I guess like here's where I'm stuck, right? Is that what it sounded like when you're describing this is that they ended up predicting that something's going to be too bright from what they put in there.
I believe, yeah. Okay, yeah, so let's see.
Yeah, the predicted peak luminosities.
Leading to predicted peak luminosities which exceed even those of supernovae. So yeah, these were over predictions, and this was kind of followed on for other people who did
Why?
further work on kilonova.
So
Because
why would
I think people were using their models and their predictions.
so but why wouldn't you just change the values of F?
Well, I think at this time, people hadn't observed kilonova. So people probably didn't have a great sense of it. Is that insane? Like maybe that is like a good range. It's a few orders of magnitude. And so I think there was probably not an easy way to determine that was, such a crazy, well, okay, crazy is too strong a word, such an over prediction.
But I mean, like, is it that, so this is 98, right? So it's like, we had measurements of supernova already. So then wouldn't you already know that that already exceeded it?
It does, yeah, so we certainly had measurements of supernova. I mean, this is like around the time that people were measuring, or people were detecting dark energy using supernova to do that.
Yeah, that's a great year.
Yeah, so that's definitely the case. And it does look like, to your point, people went and searched for these bright events associated with short GRBs, and that put limits on F. So at some point, people have done observational searches like you described and found, okay, F has got to be lower than what range was initially considered.
So that set the range, but the next thing that Metzger's done is that he's updating what physics goes into that equation of predictions of how bright something should look. Is that what
Yeah, so
happens?
he's derived, so this Q dot, the heating rate, he's derived from this nuclear reaction calculation of how the R process proceeds. And then he's also got some like dynamical, it would be interesting to kind of see. But it's some information about how the ejecta should, like some information about the dynamics of the ejecta. So the ejecta mass is what's producing this electromagnetic emission.
Right. And I wonder too if it's like in that first picture that you had of like along the jets versus like along the sides and how that's distributed in brightness too, right?
Yep.
Yeah. Okay, cool. Kilonova. Awesome.
Okay, yeah. So I guess this was the first time when the connection, clearly people knew about the potential connection between short GRB and these potential kilonova events, because the search was done in like 2006, 2010, these paper citations are. But here the connection between short GRBs, gravitational wave events, kilonovae, and the R process were kind of all put together.
Okay.
Okay. So another term is apparently macronovae for these events, but it seems like that's fallen out of favor.
There's another one. It's not Magneto. There's something else. Maybe it'll come up. But there's Kilonova and then there's one other thing. They're from different, like East Coast, West Coast rap kind of thing.
Yeah.
Yeah.
Hopefully it won't escalate like that did. I'll edit that out. Just kidding, I'm not going. Okay. So we've got so now we know that kind of one of the physical ingredients is what is the heating rate in terms of making predictions about the amount of light we're going to see, and also in terms of the evolution of the heating rate, how that light is going to change as a function of time. So the light curve is just a plot of the light emitted, or the luminosity of an object, as a function of time. So now we've got our heating rate. We also need to understand the ejecta opacity. So all of this material for this kilonova to occur is getting thrown off. And if that is completely opaque material, then we're not going to be seeing a kilonova. And so having some understanding of, okay, what radiation at what wavelengths can pass through the ejecta and make its way to us, that's going to tell us about the light curve in different bands.
Yeah.
So now we know, okay, in the history, that's the next thing that people are concerned about. And so at this point, we learn that there's sort of two types of kilonova. One is called a blue kilonova. So here we have high electron fraction, which means low neutron density. And so lanthanide, poor lanthanide, is a series of heavy elements that we pointed to in the periodic table earlier. That is a blue kilonova because it's more blue in its emission. And then there is the red kilonova, where it's higher neutron density, i.e. low electron fraction, and they're called lanthanide rich because those heavy elements exist. And you can see, as we'll see later in the paper, you can have both the blue and red components happening in different places of the merger ejecta. Because you can imagine this is a very extreme scenario. It's not necessarily going to be completely uniform.
How do they not just turn into like a purple kilonova? You know, like, are you able to see the distinctions enough? Like, you know, say I'm running, I'm looking at a light curve evolving over time, right? So there would be at some point kind of peaking more in the red, peaking more in the blue. Like, how do they not like mix so much that you don't get to see?
Well, I think people do use both blue and red kilonova and fit them to a single event. But I believe it's the red kilonova emission lasts longer. So the light curve, yeah. So the blue might fade away a little bit more quickly, but then you'll still be able to see the red emission. So that will tell you a little bit as they decay as a function of time, how much you have of each component in a single event.
But isn't that like, but yes, like, yes, there's definitely, you know, the red's longer.
Here we go. Here's a nice plot.
Is the opacity changing? Right. So like like if I try to like imagine what's happening and I like look at like clouds or something as an example, right? You're seeing like clouds just constantly like swirling around and changing, and the density is changing as that thing is moving. So then wouldn't you kind of be creating red and blue things at different parts of the ejecta cloud?
So to your first point, the optical depth, which is a measure of the opacity, does change as a function of time. So for those brave souls reading along at home, equation 5 describes, so tau is the optical depth, and it does change as a function of time. The velocity of the ejecta, and the kind of velocities involved here, you know, are like 10 to 40% ish of the speed of light, so pretty intense. Kappa is a constant that depends on so here we can see it's based on the lanthanide, whether it's lanthanide free or lanthanide rich in terms of the matter in the ejecta, and then m is the mass. So yeah, so said more briefly, the optical depth will change as a function of time.
And but then it's not like it's not I guess like I would love to see, probably exists. If not, I'm pretty sure you can make it really quickly. You're a wizard at coding. Kind of like I'm I'm trying to visualize the knobs you would turn of like if I wanted to create this like light curve of some emission that's happening at certain slice of density, it's going to look a certain way. But then if that like blobs of density keep changing, what does that do to the light curves over time? That make do you see what I'm
Well,
saying?
this equation has implicit in it. Let's see. Right. Okay. So we have this merger of mass m, which it just expanding at the same velocity.
Yeah.
Which is not quite what's happening in reality, right? Like as it hits the surrounding medium, it's going to slow down and lose energy. And there is an assumption of spherical symmetry
No.
here. Which, yeah, I mean, this is like a kind of a toy model kind of thing.
Which is what I always do. Yeah.
Yeah, but obviously in the actual event, there are going to be, and I'm sure people are doing like high resolution simulations in higher dimensions based on crazy geometries of what's happening with the ejected materials. You know, like people, I believe this has got to be in the paper. You know, there's going to be a disk forming as if you have like a black hole remnant. In the end, material is going to be falling onto it. There's probably other jets that are going to get created when there's material falling actively onto the black hole remnant. So yeah, like that. If someone isn't doing that work to see, okay, how does the light curve look, assuming here are the dynamics of how all of these ejected materials are moving around, then that would be interesting to do. Maybe we should jump actually to the remnant objects.
Okay.
Is that crazy?
I mean, it's on brand.
Just to establish, because I think this is like useful to know. There's like a pretty great plot somewhere later in this paper of the different remnants that can exist. So you can have a neutron star black hole merger that has no kilonova emission. Like if the neutron star is able to get past the event horizon of the black hole without being tidally disrupted, obviously there's not going to be any electromagnetic emission, or if there was, that would be pretty dang spicy. But you can have, okay, so here's some pictures of the general process. This is a pretty cool plot. So we have the in spiral of these two neutron stars in this case, them merging, and then you can have them quickly becoming a black hole, the prompt collapse scenario, or there's these two intermediate states where they're neutron stars that are going to slowly lose energy as they spin. They can lose energy through the magnetic field, a bunch of different processes that lead them to eventually no longer be supported by what's holding them up, which is the neutron degeneracy pressure of the neutrons not wanting to be exactly in the same place, and then they become a black hole. Or they can slowly lose energy but stay low mass as well. My brain just died. But stay low mass enough to still be a neutron star.
Wait, so what is the so say it just jumps to prompt collapse. It's like boom, we're done, we're one, right? And the difference between these other stages is that it's like spinning. Is it
they're spinning and losing. So part of the support, I believe it's described somewhere in this section. So for this for the HMNS, which I believe is I was about to swear. Here, we'll search for it in the paper.
Family friendly.
Here we go. This is the money stuff. Okay. So, yeah, here we go. So one of these HMNS objects, which is a type of neutron star, can be brought to collapse as it's accreting matter. So it's sort of like what people once thought type 1a were primarily is like matter accreting onto a neutron star.
Whoa, hold up, right? We've got two neutron stars smashing into each other, and in the midst of this, it's accreting matter onto it. So that's
well, no, this is the remnant. So they merge. It leaves this remnant, but then there's just all of this detritus from the merger event in the area. So it might fall back onto the neutron star and cause it to collapse into a black hole eventually once it loses enough angular momentum.
So I like this explanation. Also, tritus. I don't really know what that means, but it seemed like a really good vocabulary word in the description.
Sort of like debris.
Add that to the list of things I will add and like say every day. But I mean, like, wait, can you go back to that picture? Because it's like the thing that I was puzzling over was this order of magnitude change in energy between the different stages, right? You have like 10 to the 50 ergs and then 51, 52, and that is happening because spinning up, like the angular, it's gaining mass and it's spinning up faster. Is that what's happening here?
I think it's slowing down in speed and losing some energy, right? Like this is look at the mass scale. So M Tov, the Tolman, Oppenheimer, something that's like the Chandrasekhar limit for neutron stars, as I understand it. So this is the maximum mass for a neutron star. However, up here we've got neutron stars that are heavier than this kind of upper limit mass, because this one is experiencing differential rotation, and that somehow provides additional support for the star. I don't understand exactly how that's happening, and so it's not completely reliant on purely the neutron degeneracy pressure to hold it up, and so it's able to get a little bit heavier and still not become a black hole until it starts losing energy. And so some of the energy that was holding it up against collapse is lost, and then it is now just relying more and more on only the neutron degeneracy pressure, and then it will collapse.
So rigid rotation, I'm just moving around like this, like I'm a ball moving around.
Yeah.
Differential rotation is that there's like different layers of like rotation.
Yeah, so the equator may be rotating at a different speed than the pole. So like the sun, that's the case.
Yeah.
Right, where it's a big ball of fluid, and I guess this is one of the things that creates sunspots, I believe, where the magnetic field is getting twisted up because parts of the fluid are moving at a faster rate, at the equator. I don't actually know, relative to, higher in angle.
So I guess the energy, I guess I'm also this black
hypermassive neutron star. That's what it is. Hypermassive neutron star, and then supermassive neutron star for the SMNS.
Cherry. All right, so then the prompt collapse, that's just a black hole.
That's just a black hole. Hypermassive neutron star is the differential rotation one that you're describing. The supermassive is solid body rotation.
So but the difference between those two, the hypermassive and the supermassive neutron star, now that we know what this acronym is, like what's
holding it up? Yeah.
But what's making, so the dynamical one is like a more fluid thing versus like something that's rigid. So then why is that, what's making it more fluid? Is it that because there's more stuff accreting onto it or something? Like why is this happening?
Oh yeah, like why is one experiencing differential rotation and why is one solid body? I would guess, so it looks like this guy can evolve into, so for the listeners, it looks like the hypermassive neutron star can evolve into the supermassive. So presumably once that material has time to lose energy, settle, so lose, rotational energy, settle, it will eventually become, if it has low enough mass, it will become a supermassive neutron star. If it settles and its mass is too high, it'll just go straight to black hole.
Gotcha.
There's another good figure of mergers that maybe we'll prefer. Here, I love this figure. Yeah, so this includes the UV, which you have to see, like, you could really got to get on that object to see that emission. Okay, yeah, so the top row here is the progenitor. So either two neutron stars, neutron star, black hole.
Right.
Then the remnant that is created. So here's our favorite hypermassive neutron star that eventually collapses after some time to a black hole.
Cool.
And we've got a red kilonova component. We've got UV at first, and then we got some blue, which I guess here is coming from a disk that's forming.
Sick.
And so you should be able to constrain. I mean, this is obviously a cartoon, but you can constrain. Okay, there's X amount of blue emission, and then as you look at the light curve at late times, you get better constraints on the red kilonova emission.
Nice.
Here we've got like a magnetar type object. So we've got a neutron star that's spinning, that's magnetized, which has a ton of blue emission. And then we have just bam, straight to black hole, where it's mostly red. The red is overwhelming.
I got two questions. One, for the neutron, the magnetar, is that optical, like the disk win along the jets, or is it like everywhere? Like, would you have to be along?
I don't think it's just along the jets. This is so this, like in the toy models above, the magnetar is basically an additional source of heating. So far in this, we just showed the like heating rate from the R process decay, like nuclei decay, but the magnetar is another source of heating that is going to produce thermal emission that you see even on the kind of viewing angles that are on the side. So that does contribute to the kilonova. That's a good question.
Sick. And then why is it that for like the black hole, there's like no disk around it? Is it because like you need rotation to like have the disk be there? Like,
oh, you mean like why is there not optical?
Yeah, like, because that's the optical signatures from a disk being around the thing. So like, what happened to all that matter? Just ditched? Like, where's that? Did it just fall in a black hole?
I mean, if the black hole is not spinning, the material is going to more easily go into the black hole without producing a bunch of emission.
Well, why would it not be spinning? Is it that like the hell would stop it from, where's the braking mechanism to make it not spin?
Well, I don't know that it's completely not spinning. So here it says, in fact, to your point, here it says a slowly spinning black hole. So there's like some spin, but that it's unlikely because it's going to get the angular momentum of the original binary. So this panel at the far right, where there is a black hole with a more significant spin, is more likely, and then you do see the disks form.
Wait, that's pretty sick, because from looking at this, it's like you can't distinguish. If you just saw a spinning black hole, you couldn't tell if it came from two neutron stars or a neutron star black hole merger, because they would look almost the same, right? Oh no, they wouldn't. There would be no UV for the neutron star black hole merger. Man, that was a full conversation with myself.
No. I mean, that's a good point. So you can distinguish the two because this UV emission from the neutron precursor. And also we know that it's unlikely. I don't know if this is discussed that much in the paper, but I don't know if there's like constraints on what is based on like predicted distributions of black hole properties in terms of spin, mass, magnetic field. You know, what is the likelihood that you're going to have a neutron star black hole merger where there's going to be significant emission? I don't know how well constrained that is right now. Right? Because it's got to be a low mass black hole. No, the opposite. It's got to be a high mass black hole to get close to it where it's not going to be tidally disrupted for it to go in without issue, right? Because smaller black holes have stronger tidal effects. So if you have a neutron star near a smaller mass black hole, it's going to be more easily tidally disrupted, which is just like fancy science talk for getting ripped apart by gravity.
Oh, you're saying that the smaller black holes have more likely to be ripped apart than the bigger black holes?
A neutron star around a smaller black hole, because the gradient of the gravitational field is going to be more extreme.
Yeah, because
like the gradient is going to be like, of course, a bigger black hole is going to have more gravity, but the gradient is what we care about for tidal forces.
Yeah.
That's why in the documentary Interstellar, that one person didn't die when they went into a black hole because it was very big. Okay.
Thanks.
Yeah. I just spoiled it for the viewers out there.
Damn it. Watch Interstellar by now. It's 2022. What have you been doing? Like, let's go. Cool. It's also like really bizarre to even like form these systems. Like that's another like open research question, is like how you can create these things without them just getting like kicked out. Like to have the
it's kind of wild that you can have a core collapse supernova in a binary system and the other star can still survive.
What?
Yeah, that's wild. I mean, apparently it's happening because we're seeing we're seeing the, sorry, again, it's a family show.
Real amped up here. Yeah.
But we're seeing the neutron star merges, so we know it's happening.
Yes.
So I know we can't go through the whole paper, but for those that are interested, he goes through like many different sources of heating and eventually concludes that, from the observations we've seen thus far, the simplest explanation is that, at least for the one event that we were able to get a ton of observations for, GW, whatever it was called, 17. There you go.
You get a tattoo across your arm.
Yeah, I'm getting the tat tomorrow. The R process decay explains the light curve that was observed.
Yeah, that's pretty sick.
Okay.
Yeah, give us a summary.
So I think like some of the takeaways for like the future in terms of here we go, the final thoughts, is being able to get observations very close to the gravitational wave event is going to be really important, especially because, just as we saw in those cartoons, the emission right after is what can distinguish between whether or not it was neutron stars before or neutron star black hole. And so the optical and near infrared from, hours to a week after, that's like very important measurements to make. And then, in longer wavelengths, sure, that's important as well at late times. Yeah. There's also like an interesting challenge that I didn't realize existed, which is if you want to know, okay, well, what is the distribution of our process elements that's actually created in these events? It's really hard to take a spectra, apparently, because the spectral features for these super high mass elements can't be predicted from theory. which is surprising. Like with current computational techniques, it's too hard to predict where the line should be. And it's too hard to experimentally figure out where the emission and absorption lines should be, like here on Earth, like you do with, when you're calibrating a spectrograph, you get, oh, here's a lamp of neon, and you figure out, okay, here are the lines. Now we know where they're going to be when we measure the same element out in the universe. So that's kind of wild. But as we get sort of better, constraint on these two things in terms of theory and experiment, then you could take a spectra of the elements that are actually produced, which would be cool.
It's so trippy because I mean, like that point that you're making is like such a critical piece of how we understand astronomy, right? Is that we like spectra are these, we're gonna look at a thing through a prism, and we're gonna see this fingerprint in that prism, and we can look at stuff in a lab and create that same prism to say, okay, that's full of hydrogen, that's what helium looks like, that's what, I don't know, neon, whatever, and it creates these very distinct signatures. But then it's like these heavier ones, it's like you can't even like capture them in a bottle, really. And it's like so fine resolution to see any of those fingerprints from whether or not you captured a bottle of one of these lanthanides. Did I say that word right? I don't even know anymore. Like capturing those like heavier elements into these bottles to like look at what the spectra is. It's like even that precision is just wild. And then to measure it is like we're going through, like there's like, where's that, it's like that picture of the absorption that our atmosphere does, like is in very distinct wavelengths. So the like the water just absorbs like a whole bunch of stuff, right? And actually the most critical range for us to understand stuff. So to try to even pick out from the spectra that you do get and the stuff that gets like absorbed away by our atmosphere, and then to have the right resolution on it from the astronomical side is just freaking trippy, like when would we be able to measure this? Like my little experimentalist nerd brain is like, what instrument would you make for this, like to get that?
I think it was mentioned in the paper that some of the next generation gamma ray telescopes, I believe it was, are going to be able to detect emission lines from, like, obviously in the gamma ray, from potentially some of these art process elements. And so you could get, in fact, we could find where that is. Actually, no, this is going to be insane to find. No, just searching spectra in a paper like this is not going to be helpful. Or gamma ray. Yeah, that's not going to help either. That's everywhere.
But it's like, is it maybe you know this is like the resolution on a spectra, is it a readout question or is it a detector question?
Oh my god, I found it by searching KUV.
Yes.
Pro move. Okay. Yeah, okay. So you can see gamma ray decay lines from our process elements. And you could see them with, so with future gamma ray satellites. So yeah, so there are some, God, who knows what this is? SN?
It's not, I think so.
What's SN?
Oh, there it is. It's in green. Dark green. Go up. Yeah. 10.
Wow, I should know that. That's embarrassing. Whatever.
I remember like 10.
I knew this when I was doing like high school chemistry. But
I've ever remembered stuff like this. Anyway, whatever.
Okay, yeah. So from tin, that we have some predicted spectral lines in the gamma range, so in the KUV range, hundreds of KUV range, and so you could potentially see those in next gen satellites.
I don't know. I just feel like that's so cool. It's like now, like when I'm looking at a tin can, like I know that it's coming from like this astrophysical object that's happening.
Everything goes back to kilonova.
Killas. Dang. Cool.
Yeah, they're pretty interesting objects.
Yeah, absolutely.
Okay, I realized I didn't do this paper justice, but you know, I hope that we learned a few things about kilonova. Maybe we can explore some more aspects of kilonova in the future.
Yeah, big shout out to Brian Metzger for writing a review paper that people not directly in this like subfield of astrophysics can understand. And we know why things have happened in the past, what we're looking for, and just like how dope this is in the context of it all. So thanks, Brian Metzger.
Brian, you're a real one.
And all the scientists who are cited in this and all of the work and your brain power that you put into helping us understand what's out in the universe. So shout out to all of you as well.
Nice. It's a good sign off. Well,
right.
For those two out there who are still listening.
Yes. Thank you all for listening. We are the Queens of Physics. I'm Brittany.
If you want us to read a paper, oh, and I'm Jen, but if you want us to read like a really cool paper, drop it in the comments below.
Hey. Awesome. Take care, everyone.
Bye.